Hello and welcome to the first demo of chip testing results for the hardware security project. I would like to thank many collaborators and sponsors of the project in the past 4 years. In this project, we fabricated 2 test chips as a demo of the hardware security concept by logic locking. The first chip architecture is shown here. It contains 10 benchmark designs of various complexity. For each benchmark, the chip contains the original version without any obfuscation and 3 levels of obfuscated versions of each design: a low obfuscated version, a medium, and a high obfuscated version. The obfuscation is done by lookup table-based obfuscation, and the low and medium obfuscated versions use if-use type lookup tables for obfuscation, and the high obfuscated version of a design uses an SRAM lookup tables. Since there are many benchmarks included in the design, there is not enough ports to connect each benchmark independently to the top level, and therefore we have a general purpose I/O block that does multiplexing of the top level I/O pins to a selected benchmark. So at any given time, using an address, we can select only one benchmark to be tested. This chip was designed in TSMC 65 nanometer. This table shows the list of benchmarks included in this chip. It contains several popular encryption engines like AES, DES, SHA-3. It contains several state machines, B01, B02, B04, and B12 benchmarks, an ALU, and an 8-bit microprocessor. This is the architecture of chip number 2. It's a RISC-V processor core. It's an open source processor core. This is the layout of this chip in TSMC 65 nanometer. These chips got fabricated in TSMC 65 nanometer. Here are the die photo of the chip number 1 and chip number 2. And in this picture, you can see the packaged chip. To test the chip, we fabricated PCBs. There are 4 PCBs in this image. We need to test the chip using test instruments as well as FPGA. So there's one PCB with necessary ports for connecting the chip to digital stimulus response and logic analyzer, and then another PCB with FMC port for connecting to FPGA. So 2 chips, 2 methods of testing, therefore totally 4 PCBs were designed. This figure shows the FPGA-based testing setup. Here we are using the Area 10 FPGA board donated by Intel, and this is the PCB, the custom PCB we designed to host the chip. There is a socket on the PCB that allows us to put any chip we want to test inside. There is an FMC cable that connects the pins of the chip to the FMC port of the FPGA. The chip needs 2 power supplies, an I/O voltage of 1.8 volt and a core voltage of 1 volt. So we use 2 power supplies to power the chip. We have designed a tester that gets programmed into the FPGA for testing the chip. This figure shows the architecture of the tester. The tester uses 2 memories: an input pattern memory that stores the patterns to be applied to the chip, and output pattern memory that stores the patterns expected to come from the chip, the expected values. A comparator compares the patterns from the pattern memory and the responses coming from the chip. A controller provides address to the memories and monitors the comparator output to determine whether the chip is functioning correctly or not. The controller has a complex state machine. It needs a clock. The source of the clock to the controller is provided via a clock divider. There is a clock input to this design called clock tester that will be tied to the FPGA reference clock. The controller provides 3 clocks inputs to the chip. Those are chip clock, which is the main clock of the chip for functional mode. There's S clock, which is the clock used for serially loading the key bits into the SRAM lookup tables, and F clock, which is used for serially loading the key bits into the if-use based lookup tables. There are several inputs to the tester. Address 0 and address 1 inputs select which version of a given benchmark to be tested. The original, low obfuscated, medium obfuscated, and highly obfuscated versions can be selected by address 0, address 1 inputs. The start test is an input that once applied will start the functional testing. SRAM keyload input, once activated, will start the process of serially loading the SRAM-based lookup tables. And fuse keyload, once activated, will start the process of serially loading the key bits into the eFuse lookup tables. The controller outputs are as follows. Test done output indicates the completion of functional test. Test pass indicates whether the functional test passed or failed. SRAM done indicates the completion of loading of the key into SRAM lookup tables. SRAM pass indicates successful loading of the key bits into the SRAM lookup tables. The controller reads back the loaded values to check whether the loading was successful or not. Fuse done indicates the completion of key loading to eFuse lookup tables, and fuse pass indicates successful loading of the key into eFuse lookup tables. For us to be able to interact with the tester, we need to tie these inputs and outputs into switches and LEDs. So this picture shows these pin assignments. We have used the LEDs on the FPGA board to connect to various outputs that the tester provides. The test done, test pass, SRAM done, SRAM pass, fuse done, fuse pass are tied to the LEDs. The three inputs to the tester are applied via push buttons. The start test, SRAM key load, and fuse key load are assigned to these three push buttons. Address 0 and address 1 are assigned to two dip switches, which allow us to select a desired version of a benchmark to be tested. 00 configuration would select the original version of a given benchmark, 01 the low obfuscated version, and 10 medium obfuscated, and 11 high obfuscated version. Remember that the low and medium obfuscated versions are obfuscated by eFuse lookup tables, and the high obfuscated version by SRAM lookup tables. This picture shows the first successful functional test of the original version of B01 benchmark of chip number 1. We start the test by pressing the start test push button, and we should expect to see that the test done LED goes on, indicating that the test is completed, and we should also see that the test pass LED goes on, indicating the test is successful. Notice that the address switches need to be set to 00 to select the original version. Since the original version is unobfuscated, it doesn't need any key for it to pass the test. Now we are going to actual live demo of these various tests. For this test, we don't need to program the lookup tables, and now we can just start the test by pressing the start test button, and we see that the test done LED turns on, indicating the test is finished. The test pass LED also turns on, indicating that the test was successful. In the next step, we will test the obfuscated versions of the same benchmark, but first we need to load the key. If we test, for example, the obfuscated version as of now, the test would fail. For example, here we are selecting the obfuscated version of the B01, the low obfuscated version of B01, by switching the address to address 01 with the dip switches. We change them. Now if we run the test, this test will fail. As you can see, we press the switch, the test done is turned on, indicating the test is finished, but the test pass LED stays off, indicating the test was not successful, which makes sense because the LUTs are not programmed yet. Now we are going to load the key into the SRAM lookup tables. We start by pressing the SRAM key load button, and we see that the SRAM done LED turns on, indicating that the SRAM lookup table loading is finished, and the SRAM pass LED also turns on, indicating that the SRAM loading was successful. Now that the lookup tables, SRAM-based lookup tables, are successfully programmed, we can test the design that is obfuscated by SRAM lookup tables. By pressing the start test button, we'll see that the test done LED and the test pass LED turns on. Notice that we have switched the address to 1.1. Those switches are switched to 1.1 to choose the highly obfuscated version of the design, which is obfuscated by SRAM lookup tables. The SRAM lookup tables, once programmed, they return their value as long as power supply is present. So if we reset the tester, the SRAM key loader, we can rerun the test and still it should pass. As you can see, we press the start test button and we'll see that the test is done and the test has passed. That is because the lookup tables are SRAM based, that once you program and power supply is not disconnected, they continue to hold their values. In the next step, we are going to test the eFuse based lookup tables. So we are going to first load the key into eFuse lookup tables. We press the fuse key load push button and we see that the fuse done LED turns on, indicating that the eFuse LUT loading is finished. We also see that the fuse pass LED turns on, indicating that the eFuse loading was successful. Now that the key has been successfully loaded to eFuse lookup tables, we can test the low and medium obfuscated versions of B01 that are obfuscated with eFuse lookup tables. By pressing the start test button, we'll see that the test done and test pass LEDs both turn on, indicating that the test was successful. Now we can also test the medium obfuscated version of the design by changing the address to address 10. Now this selects the medium obfuscated version of design by eFuse lookup tables. Now if we run the test again by pressing the start test button, we see that the test passed as well as the test done LEDs go on, indicating the design passed the test. We are in this tester, we are not programming the one-time programmable eFuses. We are actually loading key data into the latch stage of those eFuse elements. These latches behave differently than SRAM lookup tables, meaning that if we reset the loader, they lose the data. So here we are resetting the fuse key loader. Now if we run the test, the test fails. As you can see, the test done goes on, but the test pass stays off. That is due to this property of the eFuse based lookup tables, that they need to be reloaded. And we have to reload again to make the test pass. So we reload the key to the eFuse lookup tables and rerun the test. And we see that the obfuscated version of the design by eFuse passes the test. This concludes the demonstration of the testing of B01. We will continue doing more tests. In future, we will test the remaining benchmarks on chip number 1, and we will also test the chip number 2, and we will perform performance tests, speed and power test. Thank you for watching.